Data is king, right? But getting from a messy physical phenomenon, something like heat or pressure, all the way to a pristine string of ones and zeros on a screen, well, it's a surprisingly wild journey. Let's just dive right into this explainer and demystify the invisible, absolutely indispensable bridge that makes all of this possible: signal conditioning. Just look at the stark contrast here. On the left side, we've got this raw, chaotic data. It's jumping all over the place, it's packed with interference, and honestly, it's essentially useless to a computer. But then on the right, you see this clean, harmonic, perfectly usable signal. Transforming that absolute mess into perfection is exactly what signal conditioning does.
Okay, section 1, making sense of sensors.
We almost always call sensors the eyes and ears of a system, but it turns out they have a massive communication problem. Their raw electrical signals are almost never ready for a microcontroller to just pick up and use. They might be incredibly tiny, completely contaminated by noise, or expressed as a resistance that a computer literally cannot read. Enter signal conditioning. It's this essential ensemble of operations applied to that raw output. Think of it like the ultimate translator. And this is a trap so many people fall into. You could spend top dollar on the absolute most advanced sensor on the market, but if you pair it with a poorly designed conditioning circuit, your measurements are still going to be total garbage. On the flip side, a cheap transducer can actually perform incredibly well if its output is carefully amplified and filtered. It's really a foundational secret for anyone working in instrumentation.
Moving on to section 2, why fix raw signals?
So what are these raw signals actually battling? Well, there are a few major culprits. First up is amplitude. Thermocouples, for example, produce signals in the microvolts. That is so weak that we have to drastically amplify them just to hit a standard 5-volt range. Then you've got impedance matching. If you connect a high-impedance pH probe directly to a converter, you will ruin the signal, so we have to buffer it. Add in the constant, annoying fight against 60 Hz power line hums, plus the mathematical headache of flattening out nonlinear sensor curves, and yeah, you start to see what we're up against.
But the hurdles definitely don't stop there. We also have to correct baseline offsets so that 0 actually reads as a true 0. We use optical isolation to prevent these catastrophic ground loops that could literally fry entire systems. And, perhaps most interestingly, passive sensors like strain gauges need something called excitation. It's basically a precise external jolt of power just to wake them up so they can actually give us a reading.
All right, section 3, the signal conditioning chain.
So how do we systematically solve all these incredibly diverse problems? Well, we send the data through a rigorous assembly line. Looking at this whole process mapped out, you see the exact sequence required to get a reliable digital signal. Now, not every single application requires all 7 of these stages, but grasping this full ecosystem, that's what empowers designers to know exactly what to include and, just as importantly, what they can safely skip.
Let's break this down chronologically from the top. Step 1 is transduction. That's the birth of the signal, converting a physical parameter into an electrical one. Step 2 is excitation, pumping in that perfectly stable power supply if we're dealing with a passive sensor. And step 3 is amplification, taking that incredibly weak signal and boosting it up to a robust, actually usable level.
But here is a totally fascinating engineering catch-22. Amplification is a massive double-edged sword. When we boost that weak sensor signal, we inevitably amplify all the background noise right along with it. We make the good data louder, sure, but the bad data gets louder too. And that immediately forces our hand into step 4.
Which brings us to the refining stages. In step 4, we use filters to aggressively strip away that amplified noise. Boom, now we have a loud, clean signal. Step 5 is linearization, mathematically correcting the sensor's natural curve. And finally, step 6. Isolation. Before we even dare hand this signal over to delicate computer systems, we completely isolate the circuitry to protect against catastrophic electrical interference. Which leads us perfectly to section 4, the bridge to digital.
Our clean, amplified, linear, and completely protected signal has finally arrived at its destination. Step 7, conversion. The purified analog signal feeds into an ADC, which acts as the ultimate bridge. It seamlessly translates that continuous voltage into the digital domain, making it ready to communicate instantly with PLCs, microcontrollers, or massive industrial networks.
Honestly, completing this entire conditioning chain is the absolute only way to guarantee the accuracy and true usability of your sensor measurements. Without these rigorous steps, your highly precise digital output is, well, frankly, just a highly precise measurement of garbage. I want to leave you with this provocative thought as we wrap up our explainer today.
We live in a world that is completely obsessed with raw data, AI analysis, and sleek digital dashboards. But are we actually paying enough attention to the conditioning that makes all that data real? Before you can implicitly trust your pristine digital outputs, you must first verify the messy, physical journey they took to get there. Thanks so much for joining me, and keep questioning your data.